Hello, it's Keith here, and this is lesson 32 of the platform-specific series of my Z80 programming tutorials. Now, we looked at the last week at the Sega Master System and the Game Gear, and we looked before at the Game Boy. Now it's time for the CPC Plus and its hardware sprites. Hardware sprites were a very new thing to the CPC because the classic CPCs didn't have them, and they were rather unused on the CPC Plus in its day because a lot of the games the CPC Plus got were actually rather quick ports of other games like Batman that really didn't use them at all. So the CPC Plus sprites are something that's very underlooked at, and I think if we can use them right, we can get some really good graphics out of the CPC Plus by using these sprites. Although they are limited in some ways, they're very powerful in others. And one of the things they can do, as you can see, is hardware scaling. We can actually double and quadruple the size of the sprites to make them bigger. So that's something that is a real good plus for covering screen area. The CPC Plus can do 16 hardware sprites, and the interesting thing about them is they're 16 colour in all CPC screen modes. So if you're running in CPC mode 1, which is usually just 4 colour, the CPC Plus sprites are still 16 colour, and they're actually 16 different colours to the main colour palette. So in 16 colour mode, that would allow you to have 32 colours on screen, but hardware sprites allowed Chibi Akuma's, the full colour game I wrote, to have 16 colour sprites, and it really made the game look a lot better and really gave the MSX a run for its money, even though the CPC was using screen mode 1, which is really a 4 colour mode. So let's have a look at the actual sprites themselves. So as I say, the CPC has 16 sprites, and unlike systems we've looked at in the past where we define a tile number that will give the bitmap data for those sprites, that's not how the CPC Plus works. If you imagine those as being a pointer, that's sometimes a term used, the CPC sprites don't work like that. We actually have to give a full bitmap, and the sprites are 16 by 16, 4 bits per pixel, so there's a total of 256 bytes of data. Rather strangely, they aren't packed together. Usually you'd have a single byte doing 2 pixels, but the CPC Plus sprites, they're more like what's known as registers, where you actually sort of writing data into the hardware graphics system, and the result of this is the top 4 bits, the top nibble of each of the bytes that define the sprite, not only have no effect on the colour, but if we write to them and then read it back, the data's lost, it just never goes anywhere at all. So we're going to have to write the equivalent of 256 bytes of data, but there's actually only 128 bytes of useful information there, and that's quite important because we're going to kind of pack that data together as a crude compression to halve the amount of data that we need to keep in our memory to define our sprites. That's something Chibi Akuma's did, and I should point out the code we're looking at today is directly lifted off Chibi Akuma's, so you're going to be seeing what I used in my game. So each sprite has a memory address, that there are 256 bytes of data that define its pattern. They have an X position, a Y position, both of which are 16-bit numbers, and they have a 1-byte resolution. The resolution is very important because if you don't set it, you're going to have no sprite. A resolution of 0 will turn the sprite off. A resolution of 9, rather oddly, will set the sprite to mode 1, which is square pixels. So that's the most useful, in my opinion, of the sprite options. But we're going to look at the resolution in more detail later. I just wanted to tell you, don't forget about setting the resolution and wonder where your sprites are, because you do need to set it. So why are we using 16-bit numbers for the XY coordinates? Well, that's because while the sprites always appear within the bitmap area of the screen, not in the borders, we can clip the sprites so that bits of them are missing as if they're coming into the left-hand side of the screen or going off the top of the screen. And the way we do that is by defining a negative position for the sprites. So that's the reason that the 16-bit numbers are used, and that's a feature that you can have on the CPC. Now, when it comes to the resolution, there are 4 bits that are used. The top 4 bits aren't used. Bits 0 and 1 are the Y magnification. Bits 2 and 3 are the X magnification. These are relative to screen mode 2. So if we want a sprite that's set to screen mode 1 sort of pixel orientation, square pixels, we actually need to double the X resolution and have the Y resolution at normal resolution. Doubling the X resolution would set a bit 1 here, and single Y resolution would be a bit 1 here, which is a 9, which is why we need to set our sprite magnification to 9 for the sprite to be visible. We can, however, have them mode 0 layout by increasing X again, or we could have them as double-sized sprites by setting X to 3 and Y to 2. And that will give us the big sprite that you saw before. As I said, the sprites use an alternate palette. They use the palette defined by the memory addresses 6422 to 643F. But if you're using my set palette code, you don't need to worry about that. We can just define them with palette numbers 17 and onwards, and we'll be doing that today. So enough discussion of the theory, let's just get on and look at the actual source code we're going to be using. So as I've said before, this is lifted directly out of Chibi Akuma's, so I'm hoping it's pretty good code really, because it worked for my game. So the first thing we want to do is we want to actually get the bitmap data for the sprite into memory. Of course, as I said, we have 16 sprites, each of which has their own 16 bitmap definitions. And if you're having a walking sprite, for example, you'll need to keep setting this over and over again for the walking animation, unless you're going to use one of those 16 sprites for each frame of the walking, which is probably going to mean you're going to have very few sprites on the screen. When the Chibi Akuma's game was working, the way I was doing it is I was using 4 sprites for the Chibi-Ko character, player 1, 4 for the Bochan character, player 2, that's 8 altogether, 2 for the drones, now we're up to 10, and then I used 3 for the heart icons, so we're up to 13, and I used 3 for the scroll icons, so we're up to 16. So the way I did it is the drone icons would kind of rotate, or they appeared they were rotating. I was actually swapping their positions every other frame, so they were using different frames of animation, and then I was just moving them around to make it look like they were constantly spinning, but they weren't. And that was to save this time that it takes to write all of this data, because we're going to be writing 128 bytes of data to 256 addresses. It takes a long time. With the Chibi-Ko and Bochan sprite, there was 2 frames of animation, and I had no choice but to write that every single frame I wanted to animate. But what I did do is when there's 2 players on the screen, the animation halves in speed. So there's no extra performance hit to updating the 2 players, because I'm updating one every other frame rather than the single player every frame. So that was something I did to reduce the amount of load. The other thing I had to do is, because the raster interrupts on Chibi Akuma's handle the coloured switches during the screen, I can't disable interrupts for a long time. To allow me to write this 256 bytes of data as fast as possible, I'm using a trick called stack abuse, which we've covered before. This is where we disable interrupts, we change the stack pointer to a fake stack pointer, which is pointing at the destination address that we want to write to, and then we start pushing to write data much faster than any of the LDIR commands would do. So that's what I was doing. But the problem with this is you have to disable interrupts, because an interrupt would use the stack pointer, and that was a problem for the interrupt mode, because I needed the interrupts to be very fast, otherwise the color rasters would be appearing in the wrong place. So what I'm doing is I'm doing the copy of the sprite in 4 chunks. This was fast enough, but it was still giving enough opportunities for the interrupts that there was no major degradation in the screen appearance. So that's why we're doing these 4 chunks here. We are of course writing backwards. We start at 0, 0, but we would effectively be writing FF and beyond, and then we do C0, then 8, 0, then 4, 0. And this is actually represented when you look at the way we define the sprite. We're adding 7F. 7F is 127, so we're moving to the end of our data because we're pushing and reading the data backwards, which is the better way of doing things in this case. So when it actually comes to writing the sprite data, we first need to turn the CPC Plus ASIC on. The CPC Plus ASIC, hopefully you know about already if you've seen this tutorials before. If not, please see my CPC Plus palette tutorial. Effectively, the very first thing we need to do is send a special code to the CPC Plus, which turns on the Plus hardware. Then we need to turn the Plus ASIC on. This banks in this special RAM bank of memory from 4000 to 7FFF, which is all of the data we're going to need to do the job today, as you can see here. Of course, this means that our code and our source data cannot be in this data range. So we're running at 8000, so we're out of that data range today. So here we've turned the Plus ASIC on. Then we're working out the memory address of the sprite number that we need to write the bitmap data to. Our data is in packed format, so we are loading one nibble from the byte into one destination, then the other nibble into the other destination. So we're using 128 bytes of source data to write 256 bytes of destination data, because as I said before, the top nibble isn't used in the destination. As always, you can guess that Sprite Editor can do this for you with this save CPC Plus binary. That's how I exported today's sprite, and it's how I did Chibi Akuma's at the later stages. The earlier stages I didn't have Sprite Editor, but it could have done them. So this is our loop. So what we're doing is we're backing up our stack pointer here using self-modifying code to this address here. Then we are turning the ASIC on here, and then we are defining the number of writes we're going to do. So we're going to do 16, but effectively we're going to write 32 bytes and read 16 times. We're doing a few writes at a time here because we need to be as fast as we can, so it's an unwrapped loop to some extent. I had to really balance the speed and the memory that I could waste at this point. So you can see here we're reading in a source byte and we're loading it into E. Then we're shifting the bits 4 times, so we're effectively swapping the nibbles and we're loading it into D. Now remember, the top nibble doesn't matter, it won't have any effect, so we're not wiping any bits with ANDs or anything here. So at this point we've converted one source byte into 2 destination bytes, and this push DE command is writing those destination bytes to the address that we specified in HL when we executed here, which is the address of the sprite memory within the ASIC. So we've done one pair of bytes here, we're doing another pair of bytes here, but just to save some time rather than doing too many DJNZs, and then we're repeating around here 16 times. At this point we turn the ASIC off, enable interrupts and restore our stack pointer. Now it's important to notice when we enable interrupts here, interrupts don't actually enable with an EI command until after the following command. You can check the Z80 documentation on that if you want to see, but it's definitely true. And so if interrupts enabled within this false stack pointer, we'd have problems, but with this correct one we'll be okay. So that's how we are doing our stack pointer. And so here we've got a fast way of writing data to the ASIC memory using the stack pointer to cheat, but it will just mean we have to do it in 4 chunks. Setting the sprites very similar. This is where we set the XY coordinate and the scale. So again, we need to turn the ASIC on. Then we need to work out the byte position of the data for our sprite. Now they're set so there's 8 allocated bytes for each sprite, but we actually only use 5 of them, and we do this by doing 3 RLCAs. Then we set the top memory address to hexadecimal 60 and the bottom address to that calculated definition. And you can see here that in the case of sprite 1 it will be hexadecimal 6000, then the second one will be a hexadecimal 6888. Now the numbering we're using here starts at 0 as our sprite number, so we will be getting the correct one here. Now once we've calculated the correct destination address for our data, we can make a start. One thing I am doing is I'm working with a single byte for the X coordinate. I said the X and Y coordinate are 16-bit. That's definitely true, but for simplicity I wanted to work in 8 bits for Chibi-Akimas. So what I'm doing is I'm using an X coordinate of 0 to 160, so effectively mode 0 coordinates. But to do this I need to multiply the X coordinate by 4. I do this by adding HL to itself twice, and then when we get to this point we've got our X coordinate quadrupled. So we load in the 2 bytes, which are now in DE, into HL here, because we swapped DE and HL over here, so HL is now our destination and DE is now our X coordinate. Then we do our Y coordinate. Now our Y coordinates are going to be much lower, 0 to 200, so we don't have to work in 16 bits here, but we do need to be able to cope with the negatives. The chibi character could be partially off the top of the screen in certain positions, so I had to check if the single byte we had been passed was over the possible maximum bottom position of the screen, in other words over 200, and if it was, then I had to change that top D0 from a 0 to a 255 here, and that's what I was doing. And then once we've done that, we can write the now Y coordinate as a 16-bit number, and finally we just need to set the scale of the sprite, or if the sprite's off, because if this is a 0 it will be off, and then we turn the ASIC off here and we return. So that's all there really is to it. Now you should notice I'm disabling interrupts here. I'm not really enabling them at the bottom. So if you need to enable interrupts again, you should do that yourself. I kept them disabled because I thought it would be generally safer, just in case you are doing multiple sprites in one go. Because of course this is very fast. It's nowhere near as slow as actually defining the bitmap data. So what's our procedure for getting our sprite to the screen? Well, the first thing we need to do is turn on the CPC Plus features at all. And that's this command here. That's not the same as this command here. That turns the ASIC on. It's a much longer command and it's part of the CPC palette data. And effectively we have to send this set of bytes here to this port here. So that's the first thing we have to do, and that just turns the features on. Next, what we need to do is we need to define our sprite. We're just defining one sprite, and so we're using sprite 0 here, and we've got our sprite data at the bottom of this file here. You can see it just here. But we do need to add 127 because we're starting from the end of the sprite data and going backwards. Once we've defined our sprite bitmap data, we can put it on the screen. So here's our XY coordinate, here's the hardware sprite number we're altering, so the same sprite as here. And here is the scale. So let's try a different scale this time. Let's try 1001, which is 9. Now, if you were listening, you'll know what's going to happen. So now we need to set a colour. Now, rather oddly, we're setting colour 3 because this is coloured in with colour 3. And we're setting it to white, but of course we could use any colour here. Of course there are 15 colours. The 0 colour is always transparent. And so the result is the sprite is now single-sized and it is in cyan. We do have a variety of options here though. We could have set X to 0, 1, and now we effectively had a mode 2 sprite, even though the screen is still in mode 1. I personally find that a little bit of an odd shape. I like the square pixels, I don't really like the funny shaped ones. But of course, as I said before, if we set this to 0, we have no sprite at all. And this allows us to very quickly turn the sprites on and off as we require. So there we go. CPC Plus sprites are pretty powerful. Now there is one thing you might have noticed earlier. I said that I was using 8 sprites for the players, 2 sprites for the drones, 3 sprites for the heart icons, and 3 sprites for the scroll icons. Now in 2-player mode, there's actually 6 heart icons and 6 scroll icons on the screen. So I'm over 16 sprites there. How did I do it? Well, this is a trick that you often see in computer games and things. And what you do is you reposition the sprites while the screen is redrawing. So you wait until the top half's been redrawn, you move 6 of the sprites to the bottom of the screen, and then they're drawn again, and then you move them back to the top again for the next screen redraw. This is common in all systems, and especially on the Commodore 64, and you can do this on the CPC Plus as I just described, but the problem is on the CPC is because the bitmap data defines the image, there's no pointers of any kind, there's no tile numbers or anything, you can't really change the sprite's appearance because there isn't time. So you can move the sprite, but you can't change the appearance. So you have to be quite clever if you want to use it. The way I did it was pretty easy to do, just moving the sprites once during the screen. But a more advanced game is the Prehistoric 2 game. There were some trees, and what they were doing is the entire tree trunk was a hardware sprite, and it was a single hardware sprite they were repeatedly moving the Y position of to make it look like a big tall tree. And because trees all look the same, you didn't need to change the sprite data. So you have to be quite clever if you want to use them. You know, if you're doing sort of a ball or something that you're not going to notice is the same sprite in any negative way, you can move the sprites around, but you can't make a game with hundreds of different looking enemies all doing hardware sprites and repositioning them. It's not going to work. So there you go. That's the features the CPC Plus sprites offer us. They're very good, and you know they really made Chibi Akumas look great on the CPC. So I definitely recommend you have a go with them if you get the opportunity. But of course, if you're going to release the game on a non-CPC Plus as well, you're going to have to find some alternate sprite routines to do the work for you on the regular system. Anyway, I hope you've enjoyed today's lesson. Thanks for watching today, and goodbye.